Hello, Chemistry 12. Today, what we're going to do is we're going to go back to titrations, and we're actually going to start incorporating things that we learned in terms of buffers and hydrolysis and incorporate it into titrations that we had talked about a few days ago. Now, recall with titrations, when we went back, let me see, where's the titration here? Okay. Now, remember in our notes, it says there was a drop by drop addition of a known acid to an unknown base or vice versa. So the first question is, how do we get our known acid or known base to start this particular process of titrations? Okay, now, first of all, a known concentration that we use for titrations is called a standard solution. So a solution of known concentration, this is called a standard solution. All right. Why is it called a standard solution? Because all of our calculations will be based upon this one known concentration. So that is what we call our standard. Now, standard solutions can be made from a couple of processes. One of them is diluting a stock solution. Now, when we do a stock solution, it goes back to Chem 11, where we have M1V1 is equal to M2V2. Now, what does a stock solution mean? A stock solution is just a high concentration solution. Okay, so when we say we have a stock solution of something, that means it's just a high concentration solution. Now, the other way is to dissolve a non-hygroscopic solid. And what is a non-hygroscopic solid? Is a solid that does not absorb water from the air and into a specific amount of water. And this is where we use our calculations. Molarity is equal to moles per liter. Okay. Now, why is it important not that it doesn't absorb water from the air? Is because if it absorbs water from the air, we actually get a heavier value. And as a result, it will mess up our calculations because of the addition of water. Now, so how do we do this? So just like in your titrations that we use a pipette and a burette, when we're making standard solutions, we use something called a volumetric flask. And a volumetric flask is basically a very fancy dancy beaker to hold a specific amount of liquid. So what we do is we first put a certain amount of solid in this volumetric flask, and we add enough water till it reaches this particular line. And at this point in time, once you hit that line, this is the volume of solution to 2 decimal places. So the amount of precision and accuracy using a volumetric flask to make a solution is a lot more accurate than using a graduated cylinder or a beaker like what you're used to before. Now, what you can do is if you take a look, there is a YouTube video, and I have the link right here, that shows you how you use or how do you create a standard solution using this process of dissolving a solid and using a volumetric flask. Okay, so you can try that out, or you can just watch it. It's a couple of minutes long. All right, hopefully nothing too onerous. Now, when we call, there's another definition you should be aware of. It says that the original solution used for all subsequent calculations and titrations is called a primary standard. Okay, so the original solution used for all subsequent calculations is called a primary standard. Okay, So this is just a little bit of background information about some of the language used in titration, as well as how do we get some of our known concentrations. Now, at this point in time, there are three general types of titrations that we have. One of them is a strong acid, strong base. And what you have is an equivalence of pH of 7. Now, this is key for a strong acid, strong base. At equivalence, you always get a pH of 7. Now, first of all, remember what is equivalence? It is basically when the moles of acid equals moles of base. So in this case, when the moles of H plus is equal to the moles of OH minus 1, what we get is we get neutral because no hydrolysis. Okay? In other words, it's a pH is equal to 7. Now, again, why is it neutral? Is because, yes, moles of acid is equal to the moles of base, but the ions that are produced from this particular double replacement reaction do not react with water, so the pH is equal to 7. Now, what we have here is we have something called a titration curve. So what you have is you have a pH on the left, on the y-axis, and the amount of, in this case, NaOH added on the x-axis. So if we were to plot every single point during this titration, we will notice that we get a large change in the pH from about pH of 4 all the way to about pH of 7. Now, pH of 10. And if we take sort of the average here, all right, this is what we call the equivalence point. So in the middle of this big change in pH, you have about a pH of 7. This is characteristic of a strong acid, strong base titration. Now, one thing you will notice is when you, in the middle of this big change in pH, if you look down the x-axis to the x-axis, what you will see is you will see the volume here needed to reach equivalence. Okay? Now, one characteristic that you should be aware of is because there's a large change in the pH, you can basically use any type of indicator in this particular reaction. And in this case, this is almost like our titration lab. That we did in class. So if we were to plot the pH of all the data points, we would get this type of curve during this titration lab that we did in class. Now, you might say, well, Mr. Chan, how are we supposed to calculate all these little data points? So let's say, for example, here, or here, or here, and so on. It goes back to when we did the pH, this type of calculation. All right, so what you have solution A added to solution B, and what we do is we find the moles, and then we do which one is in excess. So we could technically calculate every single data point here, all right, using that particular calculation, but we won't. All right. Now, the second type of titration is when we have a strong acid, weak base, or a weak acid, strong base. Now, for these ones, at equivalence, the moles of acid is still equal to the moles of base. That's what equivalence means. But pH does not equal 7 because the salt that is produced undergoes hydrolysis. Okay, now, so what happens here? If we have a strong acid, weak base, what we have is at equivalence, pH will be less than 7 because of hydrolysis. Now, so again, it has to do with the ions that are produced. What are they going to do? All right. Now, if we were to plot the pH versus the amount of, in this case, of acid produced, you will notice that there's a little bit of a shift in where there's a large change in the pH value. So if we take a look here, right around here, okay, versus right around here, and if we take the midpoint, notice that the midpoint is a little bit less than 7, in this case 5.27. So what happens in here, the reason why it's a 5.27 at equivalence, and I'm going to repeat it again, is due to hydrolysis. I'm just going to put hydro here. Okay. Now, again, the moles of acid is still equal to the moles of base, but the overall solution is a little bit less in terms of the pH because of what the ions are doing in the solution. So in this particular case, we have to be a little bit more careful in which indicator to use. So if you take a look here, methyl red changes color around that particular pH of 5.27. And so this one would be more appropriate than phenolphthalein. So notice phenolphthalein changes color at about, oh, I don't know, 9. And so as a result, it changes colors way before you reach equivalence point. And so therefore, it's not an appropriate indicator. So here, when you have a weak acid, strong base, or strong acid, weak base, we have to be a little bit more particular in which indicator we use. And again, how do we know that? We take a look at the indicator chart and we look at methyl red. And if we take a look at methyl red, you notice the pH range is 4.8 to 6.0, which falls on the equivalence of that particular titration. Okay, so again, notice the difference here. When we had a strong acid, strong base, it didn't matter because the change in the pH was so extreme. It went through a range of indicators. But for a strong acid, weak base, we have to be a little bit more specific. Okay? Now, there is one thing for you to be aware of, and it's this thing called the buffer region. So here, the buffer region, this is little change in pH. Okay? Now, you might say, well, Mr. Chan, what about down here? Notice you don't change the pH very much down here. This is not buffer. Because the reaction is over. Okay? But still, what you have is, in this case, if we look vertically down, we are able to see that in this case, we added 40 mils to reach equivalence. Okay? Now, The last one I want to talk about is a weak acid, strong base. Again, in this particular case, for weak acid, strong base, at equivalence, pH is greater than 7 and due to the ions. Okay, so in this particular case, if again we were to plot the pH versus how much NaOH was added in this particular case, what you will notice is the pH range is around greater than 8 at equivalence. So in this case, if we take a look, phenolphthalein would have been the appropriate indicator because it changes pH around that particular pH range. It changes color around that pH range. Brahm Crescel green would not be a good indicator because notice it will change pH, it will change color way before the equivalence point. And what you will notice here is, if again you look down, you can see that it's 25 mils that's been added. Okay. Now, in this particular case, by looking at the titration curves, you can also see what you added, what you started off with, and what you added. In this case, you notice I started with a pH of around 3, so I know that I started with an acid. Okay. Up here, notice was a pH of greater than like around 11, so I know that it was a base. Now, the starting pH, you can only tell if it's acidic or basic. Okay, in this case, it can only start as an acid down here. All right, by looking at the equivalence point and where that range of equivalence point is, then we can tell it's a weak acid. And we know that the pH starts to go up, so therefore we've added a base. Okay, so it goes down here. So when you have a titration curve, what information can we get? You should know what type of titration it is. Okay, we only talked about the 3 types: strong acid, strong base, strong acid, weak base, strong base, weak acid. All right, what is the starting material? Are you starting with an acid? Are you starting with a base? What are you adding to it? What is the pH at equivalence? Okay, so be able to identify what the pH at equivalence is. What is the volume to reach equivalence? Okay, what is the buffer region? And what is the appropriate indicator to use? All right, so when you are given a titration curve, you should be able to identify these 6 things for your information. All right, ladies and gentlemen, this is an introduction to titration curves. And on another video, I will be showing you the calculations on how to deal with titration curves. Okay, and yeah, that will be it. All right, folks, thank you very much. Have a good day. Bye-bye.